purpose, on the other hand, has to do with those discrete, okay? And with possible global rephasing and change of phase. So, and therefore are related to the fermion or to the Higgs sector. And as I said, we can also distinguish some of them which are really exact and some of them which are broken only by small prediction. So, in the scalar sector, which is the sector of the Higgs only, there is essentially only one accidental symmetry which is important, which is the so-called custodial symmetry. What is the custodial symmetry? See, this is our potential, okay? And okay, the potential depends only on so let's look at only at the potential, and maybe let's look at the full Higgs part of the Lagrange, which is the kinetic term minus the potential. And okay, here I put the covariant derivative. For a moment, let's ignore this covariant derivative. Let's treat it as a normal derivative. So these things depend only on basically on phi delta phi. Phi delta phi is the potential. If it's invariant, we can rewrite the field. The Higgs field is a complex doublet. It's a doublet with given at a charge. Usually we write in terms of the charge components of P plus, phi 0, and as we said briefly yesterday, we can also make we can build another doublet which is not independent, which is this phi c, which is just I equal to phi star, which so this is just a way to reshuffle the component such that this has transformed also as a doublet because basically it's the symmetric combination, but as other charge minus 1/2 because the phi star. Okay, so again, it's not an independent field. It's the same field, just rewritten in such a way that basically take the conjugate and for transform still as a doublet, but as opposite other charge. It's clear? On the other hand, if I want to be more geometric, I can write this component as like phi 1 plus I, phi 2, phi 3 plus I, phi 4. Now these are all real, because this is a complex field with two components are essentially 4 real components. And this potential, even depending on phi delta phi, basically it depends only on the modulus of phi, and the modulus of phi is just the sum of 4 terms. Well, so it's the radius, okay? Which means there is an O4 symmetry, okay, on the potential. And also the covariance here is just the sum of them. So there is this, and this is accidental. We didn't put this not SU2. So the symmetry we want to have is SU2 left and hypercharge. So these are 3 generators of SU2 and 1 generator of hypercharge, 4. This is 6 generator, so it's more. Okay. This symmetry, interestingly, is isomorphic to SU2 cross SU2. Actually, let me call them like this, so it will become clear. So one SU2 is our SU2, and the other is an extra SU2 which is not there, okay, but comes out automatically in this Lagrange. And to understand what is that SU2 right, I can understand it if I rewrite, I introduce a new object, and call it sigma, which is phi c phi. So I just put my conjugate doublet, and then I put so I take the 2 vectors in SU2 space. So this becomes a matrix with component phi 0 star minus. So this is still again is our Higgs field, okay, rewritten in a more fancy way. And this Higgs now, if I ask how it transforms this Higgs field under my gauge symmetry. You see, these are both SU2 doublet, so this will transform as V left sigma under SU2 left. Because just 2 doublets, they both transform like this. Sorry if I go too fast, tell me. Now, how it transforms under hypercharge? Under hypercharge, that's the thing why we put it like this. Under hypercharge, this transform as e to the minus I sigma 3, okay? Because hypercharge is, for these two fields, this is a hypercharge minus 1/2, and this is hypercharge plus 1/2. So, here, yeah, something like this, and here, okay, alpha y sigma 3 alpha is the parameter of the transformation. So under this global symmetry, you see this transform like this. The symmetry of the potential is this one, okay? But the gauged part of this SU2 right is only the third component. So this is the global symmetry, while the gauged symmetry is
the reason you prefer this notation instead to use the F304 is because you have SU2 cross U1 that is
because
easy.
I want to understand indeed what is the part that is connected to what I know, which is the left, right? Yes, otherwise I would have used U4, but then it's less obvious why. But indeed, it's very easy. Just if you think in terms of scalar, it's clear that this is O4. But then if you want to think in terms of the gauge symmetry, it's much better to use this. You see, this is an accidental global symmetry of the potential that we break already via the gauging, because the gauging we select one specific direction in the space. So again, here we have 6 generator global. We gauge only 4 of them. So the hypercharge, the gauging hypercharge breaks this symmetry. Okay? And then also the Yukawa interaction breaks this symmetry because we treat, you see that we treat phi C and phi differently, the different Yukawa coupling. The different Yukawa coupling also break the Cosetta symmetry. And actually, the biggest breaking is the top Yukawa coupling. And not surprisingly, this is the biggest breaking of the Cosetta symmetry, which gives rise to a famous observable, for those who know, which is the raw parameter. So the difference between the relation between W and Z masses, okay, which is not due to just to the gauge coupling. Actually, a consequence of this symmetry here, if this symmetry were exact and you would have gauged all of them, you would have found that the masses, so the masses of the W boson square is just d square over 4 d square, and the mass of you get exactly, first of all, you get this term here just because you gauge that part of the third generator of hypercharge. And anyway, this ratio is fixed, okay, just by the ratio of coupling. But then you get extra correction due to the extra breaking of the Cosetta symmetry, which is by the top mass. And this is a very famous precision test, which is important because it's, and you will see that when we classify operator at dimension 6, I can easily break this Cosetta symmetry. And the bounds are very strong, which then we can take an indication that if we want to have a UV completion of the model, it's better to do it such that maybe we embed the Higgs in something that has this symmetry. Okay.
It could be formulated in terms of potential
eventually, yes, but there are many possible options. Okay, and I think, for instance, one can easily think of instead of using a single SU2 doublet, you use a bi-doublet of SU2 length. Maybe this SU2 array will even gauge it and break the gauging at higher scale. Okay, but certainly is an important information. And the important information is that we cannot have big breaking of this accidental SU2 right at right. Okay, so that is, we will come back to that probably tomorrow and discuss a bit more about the Higgs. But just to this is the first example, and this is the only symmetry that we have And this is not an exact global symmetry. It's an approximate global symmetry, still very important. It's an approximate global symmetry of the scalar sector. Okay? Is an exact global symmetry if you only look at that part of the Lagrange. Then it's broken by the gauging, which is small, the breaking, and it's broken by the U-cover. But still, this breaking happens in a different sector of the Lagrangian. Then the impact on the Higgs sector is via loop, and therefore it's very suppressed. Okay.
When you say this is a small breaking, what is small there? What is the small part?
So the point is, it's a small breaking in the scalar sector. Because, for instance, maybe, okay, since you asked this question, it's maybe good to talk. What would have been, if I look at the Yukawa interaction, the Yukawa interaction that would preserve this global symmetry would have been of this form, right? Q bar left, Q right. Okay, and sorry, here you should put my X. So if, what is Q right? Q right, for instance, would be something that Q right. So if I would have only this interaction here, my Yukawa interaction would be invariant. But an interaction of this type, then I break it, this becomes super left, right? Because this is y plus. Y plus sigma right, super left. Actually, sorry, when I break it, I already select here, I will select phi c, and here I will select phi. So I'm just breaking this sigma with a bit there. Okay, since this is not really the fundamental object in the Sana model, now I break in terms of the fundamental object in the Sana model, which are U right and D right. This is what I get. You see, I call it Y plus because it tells you that there is the same Yukawa for the up and the down. A breaking term, which I have to do, minus, here I put sigma, here I put T3. This is something that do not break, that breaks, sorry, because I put one generator specifically. This is the generator of the T3 right, on the right here, which is fine for the gauge, because the gauge is only among T3 right. So this commute with the gauge is allowed by the gauge, but is not allowed by the full SU2 right. And I need it, because now if I put this, then I will get 1 minus here, I will get phi c, and this I will get it with the first component I get it with 1/2. Here I get minus 1/2. So this will be different for up and down. Maybe a more wise notation will put here at 1/2. Here at 1/2. You see that then with this y plus and y minus I can describe everything. So in the up I have y plus plus y minus, in the down I have y plus minus 1/2. So I can y up and y down and in one-to-one correspond to this y plus and y minus. Okay. Now in the standard model, all the Yukawa coupling are super small except the top one, which tells you that basically these two have to be almost equal. Okay, such that here for the top they sum up, and for the others they. So this breaking, this is a parameter that break, and so we know from the biggest breaking is experimentally we need this y minus should be roughly y top divided by 2. Okay? Because what I need to sorry, if you put it like this, y top, factor 1/2 comes from the generator. So the number, the coupling is 1, right? So it's a big breaking the Yukawa. But then if I want to look how this will modify this relation here, this will modify it via loop correction. Okay, so we'll enter in the masses of the leaf via correction related to the top chord, and therefore the effect will be y top divided by 16 pi square because it's a loop effect. Okay, it's something that I can compute precisely. And it's nice because when you compute the masses of the diamond, you can ignore all the other complicated things. If you could just work in this scalar limit, forget about all the complication of the gauge, and you just isolate this breaking term, and it's a very simple calculation, and you get this correction term. So you ask me how big. So the breaking is big in the Yukawa, but I have a very small effect in the Higgs sector. So which means so when I build my operator at higher dimension, I have to be very careful in not writing a dimension 6 operator that break directly in the Higgs sector, okay, with order 1 coupling. This I cannot do it because it will break an important property of the standard model that seems to be respected by experiment.
The effect is large because this M top is much larger than M bottom. If they were both large, for instance, 150 and 175, then the effect would be even much smaller.
Yes.
So,
and also this tells you, for instance, if we want to couple new particles to the standard model, then you have to be careful. If you put a new doublets that's coupled to the standard model or something that has coupled to the Higgs, you have to do it it's better to do it in a custodial symmetry way preserving rather than in a custodial symmetry way breaking, because then the bounds become very strong. Okay. Sorry if I was a bit fast on this. Hope you're on board. Okay, so we've seen this nice symmetry of the scalar sector. Scalar sector is easy. It's only this, nothing else. Okay, that is fermion sector is much more interesting, and not a chance because here we have only one scalar and we have 15 fermions. So clearly there are many more symmetries related to the fermion. And the story is very similar in the sense that you determine the symmetries from the gauge part of the Lagrange, and the breaking is always in the Yukawa sector. The Yukawa is nice. Yukawa Lagrange is the one that breaks most of the global symmetry. Okay? In a way which is very controlled. This is the okay. So let's look at the fermion sector. So in the fermion sector, if I look the part of the Lagrange which are not written, which is the gauge Lagrange, the gauge Lagrange part of the fermion is what I call kinetic part of the Lagrange, that is like this, is the sum I equal to 1, 3, a sum over psi along this psi field Q, U, D, L, D, psi bar I. Sorry about the I. This is the kinetic part of the Lagrange, and the part that contains interaction between the fermions and the gauge. So electromagnetism, quick interaction is all here because of the covariant derivative. You see, here this sum here implies that this thing is clearly invariant now under a global rotation in this three-dimensional space of the fermion. So I can, for each fermion species, I can do this rotation, a unitary rotation, okay, which depends. I can do it independently for the 5 different fermion species. So this U is a unitary. Which means that the global symmetry which I have here U3 to the fifth. U3 to the fifth because unitary transformation, and I have 5 of them for the 5 different species. Okay? And this is in the gauge sector. This was it. Okay. So actually we can, okay, what is here the number of generators is much more. So each U3 has 9 generators, okay? 9 times 5, that's 45 generators of global symmetries in the gauge sector only. That we didn't put. They are just because we decided to have, nature has decided to have 3 families, okay? So coming with 3 families with the same, with only 5 different type of quantum numbers means a huge global symmetry. This U3 we can recast it the following way. Actually, we can remove the global phase. So I can write this, any U matrix can only be written as a U1 phase, which for any UN, you can write it as a U1 factor times special transformation, SUN. So this is SU3 to the fifth times 1 to the fifth. Now, what are these U1 to 5? This is really not somehow related to flavor, because the flavor is here. So the mixing of the flavor is in the SU3 part. These are just global phases. So I assume a global phase for all the upright or all the downright. This one, we know some of them, right? I guess you know. We have this one. Let's do them. So one is Majorana, which is a global phase where I shift all the 3 guys which have color. I shift them in a way, and I don't shift the left. So this is Majorana. And of course, there is also Lecture number. Then there is another, which is just hypercharge. This one here, which is the one that we gauge. Then there are 2 others, that we call it A, which will be just a combination of, okay, you have 5 generators to the combination, the 2 orthogonal combination to Biron number, Lecture number, hypercharge, up to other things, and these are broken by the Lagrange. The Lagrange, you see, since I couple here Q and U, Q and D, I cannot. You see, the Lagrange automatically preserve Biron number because these and these have opposite Biron number. It's a Biron number E bar B. So independently of the Higgs, this conserve Biron number, this conserve Biron number, this conserve Lepton number. Hypercharge, you conserve it because you compensate this with 5, and that's it. The other 2 are broken on the other hand. You want this U1A, you could take it as a phase only of the D right and E right, and this one could be the phase only of E right.
Yeah, it should be one phase that is unphysical.
So,
You already removed that.
Sorry?
You already removed one unphysical phase when you rotate everything by the phase. It's not there.
Now we come to rotation. Okay, for the moment, these are symmetries that I have in my diagram. Okay, then let's discuss what is physical, what is not physical. It's a important point. So yeah, good point. So what is physical and what is unphysical? Now, okay, and also how the breaking happens in the Yukawa. The point is that the point is the following. Thanks for the question. We have all these phases of the field, okay, so which is symmetries. The Yukawa break most of them, okay? And then we can use the residual symmetry to somehow remove phases from the Yukawa. Okay. This is the point. So we have the point that we have a symmetry in the rest of the Lagrangian. We break it with the Yukawa. In principle, this Yukawa, as I told you, has a lot of parameters. Each is a complex 3x3 matrix. But given these symmetries, I can remove Okay, you basically use the broken generator to remove phases in the UCAVA and 3 parameters in the UCAVA. And this is exactly what I want to discuss. So let me try to discuss this first in the electron sector, which is so the electron UCAVA is like this. There is only one. Okay? As I said, how you know how the story works for the UCAVA. So here clearly among these U3, okay, there is here there is a U3. I can rotate this using the U3L, and I can rotate this using my U3E. Okay, so which means I can rotate this object in without affecting any other part of the Lagrangian in something that would like B to L Y E E W. Using the freedom of this symmetry here, I can go to this one here and I can choose this to make this diagonal. Okay, because actually this is a generic matrix, and so it will be diagonal YE Y2 Y tau. So, and from that I deduce what? I deduce that actually I started with something that in the rest of Lagrangian was U3 L times U3 E, and I break it to U1 to 3U1 because now I have lepton numbers separately conserved on each of. So I break these two. Actually, these are exact global symmetries of my Lagrangian. Okay. So, coming back to here this I put here total lepton numbers, but there is something unbroken here also in these things, which are exactly two combination of these numbers here, which are not at all. But now we can go one sector at a time. So now we're discussing the lepton sector, and I want to come to the counting of parameter, which is an important part. So this is the breaking structure of the Lagrangian. And looking at this breaking structure, we can understand what is physical and what is not physical in the UCAVA. So the UCAVA, a priori, how many parameters are in the UCAVA? The UCAVA is a complex 3x3 matrix. Okay? So UCAVA parameter in general will be 9 real numbers plus 9 imaginary spaces, because it's a complex 3x3 matrix, right? How many, my global symmetry before putting the UCAVA, how many generators were there before using the UCAVA? Here, U3, each 3 is described, okay, this probably you know, by 3 real coupling and 6 phases. Okay, U3 is a 3x3 unitary matrix. You probably know that the unitary, the real or 3 matrix rotation in 3 dimensional, 3 parameters, the 3 Euler angle, right? All the rest are phases. So these are the 6 phases. 9 generators as we expect for each. But I have 2 of them. So actually here I was starting with the 6 real parameters and 12 phases, but I survived, 3 phases survived then. So the broken parameter, with the broken generator, are 6 real broken generator and 12 minus 3, 12 minus 3 Imaginary faces.
Energia sta.
Okay. So these are the parameters I started with. These are the broken generator that with these breaking term I have killed. And so this gives me the counting of the physical parameter. So basically, the broken generator, you use the broken generator to remove the unphysical parameter here. And these are 3 real number and no complex spaces. And what does this 3 real number? Are the 3 lepton masses. Okay. So this counting I think is very interesting. I like to do it because then we do it also in the work. It's very powerful to understand what is physical and what is not physical. So you start with Yokohama, okay, there are a lot of phases here. There is the rephasing. Okay, this is easy. Okay, we would have done not all this exercise, but in the quark sector is less trivial. In other cases, even less trivial. But really, the thing is that when you put a term to the Lagrangian, so you have a global symmetry, you break it with certain generic interaction. If you identify which is the breaking pattern, then the number of physical parameters is given by the difference between the parameter you put in your Lagrangian and those that you use to remove broken generator. Okay, so you use the broken generator to somehow remove these physical parameters. So these 3 little parameters are the 3 leptons. Okay. Cool. So I did this because now I want to do
if
it.
you were to do this more generation,
yes.
the count will still be that you get the number of real parameters corresponding to the number of leptons.
No, this is a very good question. It depends. Well, in this simple case of the leptons, nothing changed. Okay. In the quarks, change a lot because the quark is less trivial because we have the 2 Yukawa and there is the interplay between, and then we have 3 fields and 3 Yukawa. So the counting is more trivial and change depending on the number of generations. Then we will see that with 2 generations, you don't have CP violation. With 3 generations, you have CP violation with only 1 parameter and so on. Okay.
Naturally, if you have neutrino masses,
yeah, you have neutrino masses, but this is you can do it anytime for any time. So you have to define which are the global symmetry, how you break it, and then
this is the easiest case.
This is why I want to do it in a pedagogical way, start from the easier case. Do we need to stop now?
Yeah.
Yeah. Okay, so we stop now and then we go to the work.
In case there is an urgent question, yes. We do. Okay. Vogliamo iniziare come voi? Iniziamo?
No, ma mi preoccupo se qualcuno viene in orario.
Più realisti del re. Any question at this moment? Gaetano, go ahead.
We will not do it.
I will discuss it. Be patient. 20 minutes. Indeed, your analysis is related to the violation of lecture.
Carlo,
No, it's too complicated even for me. No. Yeah. Iniziamo? Go ahead. Okay. Because so you have no excuse to go slower. Yeah.
Okay, I try to go slower. So now I want to do exactly the same exercise for the works, which again probably you all know the story, but I think it's nice to see it with this issue of the generator, which I think is interesting. Okay, so we look at the Yukawa of the quarks. Okay, for the Yukawa of the quarks. Now it's more fun because it's more interesting because now we have three fields involved, so the Q left, U right, and D right, and two Yukawa coupling. So here the starting symmetry. Now we do with free generator, we have U3 U times U3 U times U3 D, and now to make the long story short, this we break the Yukawa break it completely. So break the only thing that survives is barrier number. Okay. And as you know, we cannot diagonalize simultaneously up and down Yukawa. And this is very clear because we can, for instance, use the U3Q and U to diagonalize these, but then we fix the rotation of the Q left, so we cannot diagonalize on the left this term. And this is what gives rise to the CK method. So let's do the counting of parameters, which is interesting. So here, this group has, this symmetry has, each U3 has 3 real parameters plus 6 phases. All this is times 3, which means it's a complicated calculation. So do mistake, and we have 18 phases, but one phase is preserved. So the broken generators are 9 real parameter and 70 broken generators associated to phases. The number of parameters, each of these each y give rise to 9 real parameter plus 9 phases, and now this is times 2, which means 11 real parameter plus 11 phases. And so the counting of physical parameters is the difference between this and that. But I realize that I really small. Tell me if it is too small, okay? I don't know, especially the row under. That is 18 real parameter plus 18 imaginary minus the broken generator, which is 9 real plus 17 imaginary. And as expected, here we have 9 real parameter plus 1 imaginary. The 9 real parameter are the 6 work masses and the 3 CKM angles. 9 plus 1 phase, which is the phase of the CKM. Okay. As it should be. And I did all this because now, well, this probably you all know, you see it in the courses. Now let's repeat it for, suppose that we had 2 generations. Okay, because indeed it's interesting to see how things would change with 2 generations. We started too early, yeah? Okay. So what happens with the 2 generations? So let me, if you allow me, let me lobby and just do with 2 generators. So just with now 2 generators. So again, only 2 generators. Of course, here I would have the U2 matrix is a rotation in 2 dimension, complex. So it's only 1 real parameter. 2 dimension. There is only 1 angle and 3 phases. Because anyway, there are 3 phases in a unitary 2x2 matrix times 3, which means 3 real parameter plus 9 imaginary phases. So the broken parameter would be still final number is preserved, so I would remain with broken generator 3 real and 8 imaginary. Sorry, again, this is very bad to cancel what I and then the UCAVA, what the UCAVA would have in a 2x2, there would be a 2x2 matrix, so it's 4 plus 4, which makes 8 plus 8. So now the counting, as you can expect, is 8 real parameter and 8 phases minus 3 broken generator, and all the phases go away. And so I remain with 6 real parameter and no phases. Okay? So in a standard model with 2 generations, there is no CP evaluation. Okay? Now this is really the clean demonstration. Actually, this Khabib knew it very well. Khabib Mayani knew it very well. And when they proposed the 2nd generation of quarks, it's fantastic. But yeah, there's no CP evaluation. And the 5 is the 4 quark masses and the Khabib angle. Okay? As you expect. So, and this brings now to an interesting story. The story of the standard model with 2 generations, which I think it's a, as I said, it's a. I find it interesting because it's a somehow it's the first time in a sense in history which has lasted very short because it was somehow established in 73 or so. So after basically already in 74 there was a kind of indication of something more. But with the discovery of GEPSI, clearly the standard model with 2 generations was the reference theory. Okay? And this reference theory was perfect, a normalizable field theory that was explaining everything except one thing, which was CP evaluation. Okay? And this theory indeed could not explain it because, okay, if you write the normalizable, and at that time was considered indeed the sacred principle, you just write the normalizable interaction, you cannot explain CP evaluation. CP evaluation was observed before, it was observed in 1964. 64. So clearly it was an indication that you have to do something else. And indeed, it's as you probably know, at that time, even before the standard model 2 emerged, but there was a proposal that was the famous super weak theory by Wolfenstein, which was indeed to say, okay, we have standard model. Now is a bit of an interpretation of what was at that time. So there was a standard model, perfect, was describing everything, but we have to add something else to describe this CPU evaluation. In the modern language, that's exactly what you need to do with this effective theory. You put an extra contact interaction, like a few Fermi type interactions to explain CPU evaluation. So the idea was this. So you have the standard model 2, normalizable. Okay. That enjoys this accidental symmetry. However, the gauge symmetry allow you to write a term, which now we write like this. Super weak. And for instance, I can put this operator which I put before. Super. Right, like this is an operator which is not Hermitian, so I could have I put here a I because I want to express supervision, so I put a complex coefficient. And then I try to fit this scale to describe CPU evaluation in K-bar mixing. Okay? And anyway, I want to say, so this really is an operator which is allowed by the gauge symmetry. So this do not break any of our fundamental rules, but it breaks this accidental global symmetry because it's a symmetry that do not follow from the gauge, follow from the fact simply that I stop my counting operator up to dimension 4. When I go to dimension 6, I can break it. So if I look closer, if I expand my operator tower, it means I look to shorter distance, I can break the symmetry. And actually, nature telling me yes, the symmetry is broken. Then I get an indication of the scale. And this was with the super weak theory, the super weak scale that was determined by experiment from epsilon k, from K-bar mixing. I hope you know what this means. Does anybody knows what evaluation is? If not, we can discuss it also afterwards. So you measure something that is sensitive to this operator, you determine this scale. And this scale turned out to be 10 to the some number, remember, some number times 10 to the 4 tera electron volt. Huge scale. This is what we call a super weak. Much smaller than the Fermi scale. Fermi scale is 250 GeV. Okay, so 0.2 GeV. But this was a super weak scale. Now we know that the solution of this puzzle is the standard model 3. And in standard model 3 we can compute these things, and these I like to call it a full mirage. Right? So there is nothing there attend to that. Well, maybe there is something, but not something that explains K-bar mixing. We explain the evaluation extending the standard model to third generation, and we can compute these things. These things come from the operator like this, but two, but then have the coupling with the top right is the top. Okay, that's the one that does okay. This is a very simple calculation. You can do it. Usually, see in the books, this is done with the W. Forget it. It's completely right. Just given by the top, you can compute it in the gaugeless limit. You get more or less the right result because the breaking comes only from the Yukawa, from the top, and here what enters here is the top Yukawa coupling. Top Yukawa coupling that breaks together with all these in the basis where these are there, so it brings also the CPM matrix and so on. But it can be computed only from the Yukawa. Do the calculation, and you get something which you can determine here by what happens here is the mixing between second and third generation. So not surprising here you have BTD, ETS, where actually if you want to compute that term is the imaginary part of this object here. There is a Y, and then a loop factor. There is here something like this. Is the mass of the top. So here the only heavy scale is the top. Probably again, you go to the books, you see here G per million W to express NW in terms of this is independent of the gauge and only on the Yukawa. You can do this calculation in the gaugeless limit. I mean, we don't have time to do it. If you do it in the gaugeless limit here, these are the Goldstone boson of the Higgs of the Yukawa Lagrange. Okay, so these are masses, but the top has a mass because the Higgs don't have mass. Really, I encourage you to calculation. You get this result. So this is equal to what? So the scale, if you want, is the top, okay, which is only 174 GeV. It's nothing to do with 10 to the 42. So why I stress all this? Because nowadays, if you look at the conference, you see a lot of bounds on these effective operators. And maybe people conclude, there is nothing around. You have to be careful. So these bounds tells you where at most something should happen here, but can happen much earlier.
Gino, but this spoils completely the argument, right?
No,
So the coupling constant you can have in the not shown there could be very small. So any argument on the mass scale can be spoiled by the
no, that's it.
your argument.
If you only the point is the following. Once you so in this case, so we see, so you measure, so you see an effect which is not described by your Lagrange. So first of all, okay, you know there is something else, okay. And you get an upper bound on the scale with this because the coupling cannot be arbitrarily large. Okay? The best can be for pi and also for pi. Typically, the coupling that all the reasonable theories is of order 1, maybe 3, not more. So something before this scale should happen. Okay? And actually, in this case, it happens even the coupling is very small, happen at a much lower scale. Which is so the point is these accidental symmetries are very powerful to look for things which are not described by your theory. First message can give you upper bound when you see something. They don't give you where these things is, but upper bound is useful, right? And the positive message I want to give you that one should not be discouraged when you find a strong bound.
Yes,
especially when it comes from when it comes from a breaking or accidental symmetry, you should understand how to break the symmetry to do it in a way which is consistent. And you should not take, when people say, look, okay, since we have not seen U2 gamma, and we know that there is no new physics up to very high scale. This argument is wrong. We have not seen proton decay, but this proton decay people accept it because proton decay, yeah, maybe baryon number is violated at very high scale, but also these are the symmetry. There are a lot of the real message here is that can really, my interpretation, really can be different layers. To think that there is only one layer is really an oversimplification, which is misleading. Okay.
It was this simple. It was this simple. We wasted 15 years in nothing because this is. Allora, Kobayashi and Maskawa didn't write this formula.
Yeah.
Second thing, for 15 years, at least, the top, we didn't know which mass it was.
Sure, no,
if one had a little idea of this, then we said, top 175 GeV. For 20 years, we stayed waiting, including myself.
The message is that indeed it's not simple, and indeed we should not oversimplify. So, of course, now, posteriori, I think it's interesting to look things a posteriori to understand how something, okay, now looks simple, but again, it's not simple. And I think the super weak theory of Wolfenstein was the right thing to do. I mean, and then you see if this you can see somewhere else and so on. So it was a right approach, but also if you want is the limitation of the effective theory, as we discussed yesterday. With the effective theory are tools, okay? And then you see these things actually do not disturb anything else, indeed. And as overall as a small coupling. And this small coupling can come from a combination of some heavy scale and a small coupling, and how to distinguish the two. There is no way, okay, unless you make other hypotheses and finally you see something else. Okay, but yeah, that is the rest. And so I stress this because, for instance, now let's do the modern view. How we have the standard model 3, and let's try to now look at okay. So sorry, are there more questions about this point? So coming back to the general discussion about accidental symmetries, indeed, I hope I convince you on this fact that there is so the summary on accidental. Okay. So in the scalar section, you have the custodial. Which is an approximate. Fermion sector. If you want, we have these SU3 which is maybe okay. This is approximate, but here there is a subgroup. This is exact. We have a full symmetry here from the Yukawa. This subgroup just really exacto. The standard model for really there is this symmetry, binary number, total binary number, and the three individual lepton number are completely exact symmetry. While this only holds on the Yukawa. But the method for this, as for this one here, which are approximate, is that all the indication we have from experiment that the breaking of this cannot deviate much from what we see in the standard model. Since there are small breaking, whatever all the experiments are indicating that this small breaking structure seems to be preserved in the next layer. That is on the other hand, actually, the only clear evidence that puts some analogy to what was the standard model 2 plus neutrino standard model 2 plus configuration are neutrino masses. Because neutrino masses break lepton number. Okay? So evidence now. So neutrino masses, we have a clear evidence, no doubt, that none of these you want is exact. Actually, they are broken by neutrino. Neutrino masses are very small, so the breaking is very small. It's really remnant of the study of simple evaluation. This is why I wanted to assess it. However, to determine from that an indication on the scale is very difficult, exactly as it was difficult at that time. But let's see how we can describe it. The nice thing is clear the philosophy. So, long story short about neutrino. So what we know on neutrino mass, we clearly see that neutrino oscillate. So neutrino have a mass, and what we see in experiment are the left-handed neutrinos. Okay, because there is no doubt that with what to measure the neutrinos that feel the gauge interaction, because then we see the associated structure. So how to describe neutrino masses? Is how even here Majorana lecture, you know that for fermions we can put another type of mass which are Majorana masses. Majorana masses, we don't put it for any of these field here because Majorana masses automatically violate any charge to the fermion. So if I have a fermion here, we can have the Dirac mass which actually for all the fermion there violate gauge symmetry. This is why we don't write it like this, but we write it via the Yukawa interaction because we put here the Higgs to complicate. And then we can write Majorana mass something like that. Okay, we have to put the SU2 matrix, the Dirac matrix to make the curve, but basically it is a mass term where you have the field square, you do a Lorentz contraction such to get the Lorentz scalar. This mass, you see, there is the quantum number the phase of this field here I take it twice. So this will break any global symmetry. And there is, if you want to compensate, you have to put something here that compensates twice the charge of the first. So, and that is why we cannot write it at the renormalizable level for any of the field which is there. But for neutrino, we can do it easily if we go to higher dimension. So, neutrino are here. So we would like to give mass to this object here, right? Because this is in expression of the neutrino is part of the electron doublet as is charge assignment. It's really the same charge assignment of phi c, not phi, because here there is -1/2. Here I could put phi c. I don't put it because it's not an independent field. Phi c is exactly this, but -1/2. It's the conjugate. So, for instance, I can take this combination. Is if I do this combination, this is an object which is totally neutral from the point of view of the standard model gauge symbol. It's phi c dagger. This is a doublet, SU2 doublet. This is a doublet. So here I put the dagger, so the SU2 part cancel out, and I put the dagger, so also the charge cancel out. And when I go to the Higgs wave, remember that the wave of phi c these things when the Higgs get a wave, select exactly p over square root of 2 left. So if I take this object in stress cosmos is a combination of two fields which is totally neutral from any of H quantum number. So if I take this and I square it, transpose it, I get a neutrino mass term. So a neutrino mass term in the standard model is a typical thing that I can write, however, will be an operator of dimension phi. I can write this operator. This operator is a and let me put the coupling. So this is an operator at dimension phi written only in terms of the standard model field that when the Higgs get a wave describe neutrino masses. So this is the master that they get for the neutrino, and here I should put flavor I, A, I, A, A. It's really the same philosophy for the standard model 2 with simple operator. So we write an operator of higher, in this case, it's dimension 5. And actually, I can tell you probably, this is the only dimension 5 operator I can write. Tomorrow we'll do a complete analysis. This is the only dimension 5 operator compatible with the standard model gauge symmetries using this player. By trying to combine all these fields, in no possible way, there is only one dimensional structure, which is this one written by Weinberg in 70.
Questo 76. 77.
Not by chance, it's called the Weinberg operator. And so you have a prediction for neutrino masses.
It's the same year of Annals of Physics Phenomenological Lagrange.
I know really when sure. People started to look at
exactly
effective theories, and it's beautiful because explain naturally somehow why neutrino masses are light, because okay, here you have a ratio of scale, so clearly if this lambda is very heavy, neutrino masses are very small. Okay, this is sometimes called the seesaw, but this is usually seesaw you call it explicitly when you add the neutrinos, that we can do in a minute. But there is no need to add the neutrino. Actually, in the philosophy of effective field theory, this is how you describe neutrino masses. And as you probably know, now if I assume that this G is of order 1, it's a big if, okay, which is related to what we were saying before. If this, then if I put, then if I want to get mu of order of delta mu atmospheric, which is indication of the scale of neutrinos from the atom, then lambda nu is huge scale, really huge scale. Which again, this you can think. Remember, I can tell the first time I saw this, which was long ago, I find it beautiful. This is clearly now the same scale of grand unification, so fantastic. However, you have to be careful. Okay? It's true, could be. And if it's like this, then you say, forget it, so we will never test it. Could be. But first of all, this could be, and maybe this is the scale where you break Lepton number. Doesn't prevent that there are other scale lower where you don't break Lepton number, which would prevent you to other PSM effects. The usefulness of these accidental symmetries that allow you to partition these effective theories in sectors. Okay? So this, we have an indication that the sector violate Lepton number is somehow very secluded. Still about the scale, I think I will just conclude an interesting consideration here, which is the following. As you know, we can, and of course, actually even well before Weinberg already Minkowski and others show how you arrive to this with an explicit model, which is add the latent neutrinos via the seesaw mechanism. So we can have a normalizable Lagrangian, which is this, and then I add a Java term, let me call it y nu, of the type which is exactly like the term I have for the mass of the app. Okay? Plus, so I introduce now a new field. So I'm going beyond the standard model. Therefore, I can add a Majorana mass term for this. You're right, because now this is an object which is, as we remember yesterday, is totally neutral. So this I can put Majorana mass term without violating anything. And then you integrate out, if I assume that this M right is heavy, the story which probably you know that I have this thing, you write master, right, and these things is the one is the normalizable way to construct that operator. Okay, so I construct something a couple new left, and the 2, 5, that in that way, and I do it via the exchange of a dependency. Okay, so I can compute. So with this renormalizable Lagrangian, which is extended, so I have an extra field, extra heavy field in the limit where this field is heavy. Its effect will be exactly quantum interaction. Which is okay. And you can compute it, okay? And you can compute and you will get that I Gij over the y nu transpose 1 over m right y nu. Okay. I skip calculation. You understand? I put 2 i's the Yukawa and there is the propagator. So why I say all this? I think it's this. Once you look and you understand that maybe this interpretation of a scale should be taken with some care. Why? Because, for instance, it would be natural. This y nu, you have to make a guess on what this y nu is. The most natural guess is this is exactly like the other. So probably this is hierarchical as the one that we've seen there in the all the other fermions, right? It's exactly of the same type. And for instance, if we take the Yukawa of the charged leptons, here there are 4 orders of magnitude or 3 orders of magnitude between the electron Yukawa and the tau Yukawa. In the 4 up is even higher, and I have it squared. So here I should expect something, and suppose if this attended sector is degenerate, or order 1 degeneracy, I don't know what it is, then I should expect a huge super hierarchical structure for neutrinos. While neutrinos are totally anti-hierarchical, are almost degenerate. So it's tricky. And maybe this is hierarchical, but then this means that this one of MRI should be compensated, so should be totally non-hierarchical, and should span 8 orders of magnitude MRI to compensate the hierarchy on this. So this then it's actually less trivial that one would see there. So maybe, yeah, for 1 neutrino it could work, but for 3 neutrinos it's much more complicated. So again, life is complicated. So never reach too easy conclusion that maybe there is a, it could well be that this thing is more complicated. There are more fields, not just only these simple attended neutrinos. Okay? Because if I do just with the one simple attended neutrinos, I then have to use a very special spectrum for the attended neutrinos to get the observed masses for neutrinos which are non-hierarchical, starting from the Yukawa, which on the other hand I would expect it to be hierarchical. Of course, you can say, well, maybe the Yukawa is not hierarchical, and then not. Yes, but so you have to make a lot of hypotheses. So the truth to be agnostic, we don't know. Remembering the lesson from CPU evaluation, there is an upper bound, which is very far. So we have to be patient, but could well be that even for neutrinos, the scale is really much lower, at least for some of them. Could be that there is a attended neutrino at the TV scale, or even lower. Okay, so that was the message I wanted to give you about accidental symmetries. And now, finally, we still have 15 minutes, right?
Yes.
So finally, let me keep here. Tomorrow we'll redo the full classification of the operators, but now the last things I want to discuss today is the famous hierarchy. And I think then neutrinos plays an interesting in the so something a bit different. So sorry, maybe I should ask for other questions about what I did so far, but neutrinos and again, a bit brief here, in case we can discuss later. Hierarchy. So in the stress the other day, here in this part of the Lagrange, most of the Lagrangian, we have only marginal operator. Okay, the marginal operator are operator of dimension 4, strictly speaking, with couplings which are non-dimensional. All this coupling run with the scale according to the rule of quantum field theory, so we can write beta function. All the GI, but so the H coupling, but also lambda, also coupling. Okay, we write actually it's a structure of this type. So it's a differential equation that tells you how the scale evolved, how the coupling evolved with the energy, and actually generically is a matrix which involves all the coupling. But this is just these are all numbers that depend on the gauge coupling, and the generic solution are a solution of the type, again, in perturbation theory, you will have a coupling at the given scale, for instance, at the electroweak scale, will be this coupling at some other scale, I think lambda plus, and here there are this beta function, and then there is a log of k. Okay, something like that. I'm going faster, putting all the factors. It's just a logarithmic, the key point is the logarithmic dependence. This is what. This is true for all couplings except one, which is the Higgs mass term, the only dimensional coupling vector, because it's a dimension 2 operator, so it's an energy dependent. So for the try to do it following my notation. For the mass term there, so actually here you see I put lambda d square, but when I find I have lambda minus lambda 4 d square, and these I call it square mass term, the quadratic term. This term is the one that we measured, so the one at this scale is like this. Yeah. There are no factors. Now, here is a bit of a subtle point because, well, generically, these things depend quadratically on the curve. Okay? Probably, well, most of you are familiar that a way to do the normalization where you don't even introduce a scale. Actually, this is really the Wilsonian approach. If you think of the cutoff as the next layer of the theory, that is what you get. If you do dimensional regularization, you find 1 over epsilon. So it looks like this is a fishy, non-physical thing. It's true. It's non-physical. You can always. It's clear that this dependency is much more dramatic than that. So clearly, there is a strong dependence on the completion of the theory on this term here. Of course, you can always redefine this and say that this is cutoff dependent. We cancel that, and this is what I mentioned we spend. Okay? And I know this has to be under the GD square. However, this is what you get from just from the sensitivity, the cutoff hides a physical sensitivity on the parameter. So the fact that here it is quadratic dependence, not just an artifact of normalization, is the fact that if you extend your theory, you put something that will couple to the Higgs and is associated to some heavy scale, this heavy scale, this heavy mass, will appear in this equation. This is why I want to discuss it here in the case of dependent neutrinos. So if I do here, I can compute the correction to the Higgs mass in this simple Lagrange here. So here I extend my theory with a heavy attendant neutrino. Okay. So here I will have a correction to the Higgs mass of this type. And see, with this interaction, I couple to the attendant lepton and the attendant neutrino. So I put this interaction here. Then this attendant neutrinos as a mass. So here there will be a mass term. Means I treat the mass term as a perturbation. Always do, as yesterday. Just to understand that to conserve the wrongly. Minor mass term invert the Fermionic line, so you have to put it twice to have this loop. So you can compute. You can do it putting the full propagator. Okay. Here you write. Here you have mine. Right. Okay, from this just diagrammatic sketch, you understand that your quadratic term phi will receive correction proportional to m right square. Okay, so you compute the things, let me give you the result. I did it to be one can get convinced that what this is the correct result. So you get what we call just delta and square phi, and you get something that goes like this. I do it just now for one generation, just to you get the loop factor, and then you get this right square log of plus divergent term. Okay? This, if you do the calculation in dimensional regularization, you never see lambda, okay, the cutoff. But you see this m right square, which is physical. So here I put a physical state heavy, and you see that the mass of this physical state appears quadratically in my correction to the Higgs. That is an explicit realization of what was written here. Because indeed, the realization is a physical effect. It's how you are sensitive to the UV degrees of freedom in your theory. So the Higgs mass is quadratically sensitive to the UV freedom. So unless you invent a mechanism to screen this, and so far nobody succeeded except putting extra symmetry, like for instance supersymmetry, where you cancel these things, or assuming that the Higgs is a pseudo Boston boson, okay, you can cancel that, but then you have to put other degrees of freedom, and these other degrees of freedom should appear at a scale which is not far from V. Then you end up with these things here, and this is the famous fine-tuning problem. So it's very unnatural to think, okay, this has to be small compared to what we measure in experiment. Also because you see, I can adjust this at one scale, but then this run. Okay, so and this really gives to a physical modification of the Higgs propagator that we don't see. So it's a physical effect. So if we, and of course has to do with anything coupled to the Higgs. Of course, if you don't couple anything else to the Higgs, you are kind of safe. But if you couple, for instance, to the top is coupled to the Higgs with a big coupling. So at least the sector Higgs third generation, and in this case you will affect the two loop, but so you gain a factor of 100, or because of 1 over 16 pi square, but then at some point you will hit it. So the hierarchy problem is this fact that in this Lagrange there is one parameter which is a scale, which is the Higgs mass, and this is fixed to 246 GeV, the Webb or the Mixed mass is 125 GeV. So it is an indication that something should happen to screen this parameter from heavy degrees of freedom. So while all these other contact interaction, all these violation will tell you possible very distant scale, here there is something that tells you there is something that should happen nearby. Unfortunately, I cannot tell you exactly where, okay? Because this is a how much amount of fine-tuning you want to accept, and it depends also how you couple to the Higgs. So it's not a strict, precise argument, but it's a qualitative indication that something that coupled to the Higgs and the third generation, again, because the third generation is strongly coupled to the Higgs, this is clear. Something should happen not too far okay, from the electroweak scale. And this is the strong indication that continue to do experiment at nearby scale is motivated. This, in my opinion, is the only clear, strong motivation that there has to be something nearby.
Nearby,
nearby means TV. Okay, this means this. You see, these things. I mean, we know that this is all square. Okay, so here you can get the suppression if you put small coupling, but cannot be too small again, because otherwise you have to have something coupled to the Higgs. So the indication that there has to be something around the TV scale, can be 1 TV, can be 3 TV, already 10 TV. You have to adjust numbers with much more than 1% precision to get the Higgs mass of 125.
What about the case where there is nothing in this case? We don't have the running. We have running anyway.
No, the running is anyway.
It depends from what you see in
the running. So the running tells you how you are sensitive to this coupling here depends, for example, on the topic of a coupling. So here, for example, the limit contribution here is the topic of a coupling. But of course, if there is no, you see what others are this physical state. If there is nothing, there is nothing. Yes. The point at some point there is the Planck scale, there is gravity, and gravity has an intrinsic scale which is huge. This is the big puzzle.
Also, your work on metastability, there is also that.
Yeah, but this doesn't indicate really a clear system. So the real problem, in my opinion, is gravity. The point that nobody is able to compute precisely the gravitational correction to the Higgs boson.
Okay.
There are some conjectures.
There's at least a Planck scale.
At least there is a line of reasoning that maybe for some accident this quadratic correction of gravity will cancel, but it's a conjecture, and I think it's very strongly motivated. All the attempt to compute they find, and then anything like grand unification or these things where we really know what we are doing, we see this big effect. So any explicit QFT extension will give you exactly like this, give you a clear functioning problem. Beyond QFT, to be honest, I don't know. I think it's unlikely, but I cannot say for sure.
Let's thank Gino, so we open officially the question session.
Please.
Okay, sorry, but LSC, what is the so far from LSC?
No, okay, that is, you see, then this tomorrow we'll discuss much more about this. Indeed, I try to say especially things coupled to the Higgs and to the top, okay, or third generation. For instance, if you have something coupled, say a Z prime coupled to the electron and muon, I don't care. Will not give you something. So because this is the difference. LSC bounds are quite strong, even up to 10 TeV for something coupled to the light generation, electron, muons, up and down. For something coupled to the Higgs, if you look at just on the Higgs potential or third generation things, the bounds are really around 1 to 1.5 TeV, not more. So could really be still around the corner. I hope so. I'm strongly convinced. And this is why I think building a new accelerator will make basically one order of magnitude precision is super interesting. So if this argument is correct, it has to be there. And again, indeed, there's been a bit of pessimism because people, as usual, try to generalize and things like that. So it doesn't need to be anything around TV scale. We can have different layer, and I think my strong conviction is that there has to be a layer which involves the Higgs and the third generation at nearby scale to solve this problem. All the rest we can decouple at different scale depending on how you break these other symmetries and so on.
But let me go back when you were playing the game with the different generations.
Yes.
Now you can play the same game with different number of colors.
Yeah.
And even different groups. So now the conceptual question is how generic or how exceptional is the standard model as we know it? I know it's a merely philosophical question, but I think that your opinion as a person that is running the machine.
No, I think it's a very deep and good question, which yeah, you didn't talk too much. It's true there are certain things which are a bit peculiar, but I think I don't have. I have to think a bit more. Maybe I don't. But for sure, I think what is interesting is true that there are playing with for instance, a number of fermions, a number of colors is very interesting. It could well be, for instance, to address this problem of the Higgs, we can embed the theory and we go to more conformal windows where with the running it's changed a bit. If you doesn't seem the standard model seems to be rather non-special in the sense that if we see a running of the coupling, that they I don't see anything too special. At first sight, I would say there is nothing conformal which could have been with a more clever choice of NF and C. It would be nice because it would help to solve some problem.
Can we comment from a purely mathematical point of view? The things that Alain Kohn the standard model is quite exceptional because if you go not to group but to algebras, then they are, you may represent it as the three smallest algebra, 1 by 1 matrices, 2 by 2 matrices, real and 3 by 3 from some things, and all the representations of the particles are in the fundamental representation, which is true for algebra, not for groups. And really, the standard model comes out from this mathematical requirement that some sort of internal space is like a manifold, comes out basically uniquely, together with the Patisalan, because also this is as fundamental representation, and so, but no SU5, no SO10, nothing else.
I'm super happy to know because I'm a big fan of Patisalan, and indeed
Yes, I'm too from the time that I was at ICDP. It's because it's the most symmetric.
Patisalan is the simplest. I completely. Patisalan also really this issue of the quantization of the charge in Patisalan is beautiful.
Yes.
Okay. Really, the representation of Fermi becomes simpler, while in SU5 is much more ugly.
Yeah, 5 and a 10. So I agree with you. But in any case,
but the neutrino masses. They don't address the issue.
Well, you have to. It's true. Neutrino masses. Yeah. Also, see the point that the standard model in its simplest form, but then for instance, neutrino masses is clear an indication that there is something else. You see, this is the point that. So it looks that there are also special things about the standard model, but then indeed we also have some clear indication that has to be completed. So cannot be the end of the story. This I'm 100% convinced. For instance, especially because of neutrino masses.
This is the evidence of
this is a total unambiguous evidence. We can discuss about dark matter. Dark matter can be black holes. I mean, so there are way out about. But neutrino masses is something that is in field theory, we understand, and also this hierarchy problem. I think it's a serious thing. And whenever you try to explain neutrino masses, you see that you touch the thing and you have to extend. But then Patisalan is a beautiful way to do that. You also have attended neutrino, so it's perfect from that point of view. However, to explain neutrino masses in Patisalan only, it's more complicated. And okay, I don't want to advertise my best theory. Maybe we'll discuss tomorrow, which is my theory, but it's an extension of Patisalan. But along in terms of gauge group, Patisalan I think is a very good option.
Can you comment on the following sense that accidental symmetries that flow in a low energy theory can point to some gauge symmetry of a theory at higher energy? I'm thinking to B minus 10.
I think it might.
Groups of SO10 are taking the direction.
So I totally agree with you. So the fact that we have this accidental symmetry, which seems to be better than accidental. This is the point. So we did, because otherwise we would have seen it immediately violation. So I think the best way to have accidental symmetry is to have an explanation which is just so. For instance, in the standard model, the accidental symmetry comes because of your choice of field content and the intersection with the gauge group. So, for instance, in the Yukawa sector, I think my interpretation is that these really point to an extended gauge symmetry where you can deduce. I don't know if this is what you want to say. Maybe it's so when you can deduce this as symmetry from resulting from the gauge structure, which we cannot do in the standard model. Okay, for some of them.
Here
For example, in SO10, you have B minus L as one generator of the.
But I think this is a bit more subtle in a sense that yes, first of all, B minus L, yeah, these things are, but also on the flavor, I think this is also very interesting. So the fact that we have these approximate symmetries related to the small Yukawa coupling, I think these we can probably understand them with an extended gauge, which, however, to look at the families in a different, not act equally on the different. That would be just a charge assignment, okay, and that we'll be able to explain why light generation have maybe we'll comment on this tomorrow. But B minus L, yes, and also as you do right custodial again, fit perfect in Patisalan. So I think
which is a subgroup.
Which is a subgroup of SO10.
Be aware that in this department there is a good part of the institute that has dedicated their life on the SO10 and the potential of SO10 and on the 126, all the possible representation.
The SO10, I mean, nobody disputes SO10. The point is how you break it. If you want to go on the SU5 or on the Partisan road. These are the two maximal subgroup, right? And then they all unified in SO10. So I think
at that time I remember some breaking path going through Patisalam or SU3 cross. Who knows?
Question from other people. I have some questions.
and we also the student, yeah, also
Exactly. From the younger or less young than me.
I have a question, but it's more an advice than a question. So, what would you say is an interesting topic for a master thesis, or I don't know what to do with my life. Yeah, obviously, obviously you can be also very specific. So obviously, as the professor said, a very general topic of the neutrino mass or whatsoever. But would you say specific topic, or I don't know, which is interesting and also not solvable, but that can be studied?
I think that it's an interesting time. There are a lot of questions which I don't want to select only one topic, because I think it would be there are different things. First, neutrino mass certainly is an interesting subject to look, because it's an indication. But on the other hand, I mean, for instance, all these vapor symmetries, I mean, how to explain this accidental symmetry from the more standard gauge group, I think is an interesting direction. Actually, this is what I'm working these days. But also, explicit mechanisms to protect the Higgs by composite Higgs model is also a very interesting idea, because to protect the Higgs, basically we know only two basic mechanisms. One is supersymmetry, and the other is composite Higgs. That is, the Higgs is the Boston bond, pseudo-Boston bond. I don't think there is anything else. And on supersymmetry, a lot has been done. Okay, this is why maybe there is still more space to play in the composite Higgs direction. Now, this is not a thesis argument. Okay, then there are a lot of more, but I think it's an area where there's still a lot of development, which I think is interesting. So, the flavor, neutrinos, and the composite Higgs are three directions which maybe are also very interesting.
More question from young people. More thesis to go. I have a question.
I'm not young,
Feel young.
But okay, I like very much your tale about the super quick, but of course, unfortunately, you couldn't predict top mass there. You didn't the new BTD and BTS at the time, and you didn't know.
People try. They check. People try. I try. I looked. People trying. They got only found.
Let me tell you this. Also, this is connected to this historical matter. Was very interesting. I discussed a lot with Paolo Franzini.
Exactly. That is starting. I know that he started.
At the beginning, there was, since when the people understood, okay, third generation works of the big work was discovered, five, whatever. There was a strong prejudice that the top has to be
20 G.
Something like that, no? And then, and also you have the Cabibbo angle, which is 0.2. So then maybe the ECB.
But 20 GB was already, because after they measured BB bar mixing, because before they thought it was around the corner.
No, but even after they measured BB bar mixing, then you really have the product, and then still you don't know what the top mass is, no? And then there was this strong prejudice that this angle be another Cabibbo. I mean, why should be much smaller? And then I think it was Paolo Franzini was trying to measure BUB and only put down BUB from B decays, and then I think I remember somebody, he told me, or maybe Altarelli told me, this is wrong. I mean,
no, Altarelli 83. Altarelli 83. If you sit in your bottom, you will stay very long.
Anyway, so you see, these are there was no way, and this is.
But now on the other side, on the PMNS, because you can play the same trick from the Weinberg operator and the structure with TMNS. Can we try to extract some more information from that?
It's exactly the same thing. So it is exactly the same. So you have the overall scale, and also you have the spectrum. Okay, so clearly we know that we measure delta M atmospheric, delta M solar. We don't know which is the lower bound, but also another also cosmological bound. But anyway, if you look at between these two things, you know that the maximal separation between the two heaviest neutrinos is a factor of 6, not more. So they can be less, cannot be more than that. So they are clearly almost not the general, but it's not like in the core. Okay, so they are much more close. And also the angle, we know basically now all of them, except the phase, which I don't care too much about this phase. Okay, it's a phase. There will be a phase. So,
must be there.
For sure will be there. Then you have to make hypotheses. Also, maybe I think make hypotheses. So doing model building is good. So now I'm trying to advocate here effective theories. Yeah, effective theory are tools, but you should use these tools with hypotheses. So make attempt of a UV completion, and then use the tool to compute things and correlate this. So effective theory is good to correlate different obstacles, but then self without extra hypotheses, and you don't go far. Okay, just an infinite parameter space. So I think so. Then you have to make hypotheses, and for instance, the simple seesaw, in my opinion, not too convincing because what I said before. I really don't see. For instance, with now Andrea will work recently on a paper with inverse seesaw, which actually fit better in Patti-Salam type theories. So we have to introduce extra fermions, however, to play the game. I think this is interesting, but admittedly is an hypothesis. And this would fit well with some rotund neutrinos at the QT case. So, but to be honest, try to be unbiased. I don't know, and there is no unambiguous way. Exactly as there was no at the time. Actually, at the time, a posteriori the problem was simple, only two parameters. Yeah. Here it's more complicated. It's a 3x3, and we don't know.
Right.
M1 can be even 0. I agree. So this is why M1 can be 0, but then you see M2, M3, and if it is 0, you get the maximum separation between 3, right? So the 0, I don't think it is there would be an extra symmetry or so, but I don't think it has a big issue there.
No.
I don't. At this point, I think it's hard to think that it's 0, but can be arbitrary.
No, just discussing the
Yeah.
The hierarchy can be
I think,
very
for instance, the things now, yes, the things I would like to know more from neutrinos is some deviation from unitarity in the PMNS. That would be super interesting, because if there is something else, you should see some deviation from PMNS unitarity, which is very difficult. Okay, it's not an easy thing, but that is really what it because then if you have this extra state, it's not anymore a triple matrix. It's just a triple is a subsector of a bigger unitary matrix, so it should not be exactly unitary. But it's tough. It's similar to this. This historical analogy. If you try to see DCB from the non-unitarity of the 2x2 Cabibbo, you don't get it because it's too small. So it's not an easy game.
More question? I have some more. I'll try. Don't go anywhere. Any more question? So what did just I try to remember historically, if I remember correctly, people understood that Wolfram parameterization had a hierarchy, and indeed Frogat-Nielsen was trying to explain that. So the Frogat-Nielsen symmetry was trying to address the issue of the Wolfram parameterization, the hierarchy. So if one checks the date of the Frogat-Nielsen paper, sees when it's realized that if you want, you can do this bound you did for Anton. And the other thing that I wanted to ask is that is going back to this question: what is the new scale? I mean, many people have tried, but now we can do better. Also on sin squared theta W.
Yes.
It's how precise we are close to SO5 or SO10 and the chronological data. From that, what would you get?
But this I think makes sense only. I mean, you can predict something the W only to, for instance, if you assume
But there is, if you want, you measure some sweet data, and you see the discrepancy. So it's not that far away. So that is suspectful. And indeed, people.
Yeah, but this indeed is the fact that they did on the gauge symmetry, you don't see any deviation. Is very, very precise, which means you don't need to touch the gauge symmetry. But indeed, and I think the most protected, the most tested is really SU2 left. So the point is you have to be very careful in adding extra SU2 left charge speed. And if you do it, you have to do it in a custodial symmetry invariant. I don't think we can go much more than that.
Okay. So if there are no more questions, we can close the today for today, and tomorrow same time, same place. Okay, thanks.